start. In this lecture, I will give you the formalism of neutrino mass mixing and oscillation, and tomorrow we shall discuss details of atmospheric and solar electrolysis. Okay? So this is the plan. I start with a recap of the basic constituents of matter and their interaction, that is the matter, fermions and bosons, which together constitute the standard model of particle physics. Since we discussed it this morning, I will just use one slide from the morning stuff. Then I shall discuss neutrino, chirality and mass, and then neutrino mixing and oscillation. Tomorrow we shall discuss atmospheric neutrino oscillation, solar oscillation. As usual, we shall use the natural limits where we put Planck's constant and velocity of light equal to unity. So mass of a particle is same as Lewis mass unity, and proton mass we saw is about 1 GeV. That will be GeV will be our basic unit of both mass and energy. Clear? Okay. So this is this slide I am repeating from this morning's lecture. We saw that the basic constituents of matter are a dozen of fermions, spin half particles, the 3 pairs of leptons, electron, mu, tau, along with their associated neutrinos, and the 3 pairs of quarks, up, down, strange, charm, bottom, and tau. Their masses are indicated in red in GeV units. The mass of the charged electron go from 0.5 MeV for electron to 1.8 J per tau, spanning 3 orders of magnitude. The mass of the constituent quarks go from 0.3 GeV for up and down to 175 J per tau, again spanning 3 orders of magnitude. For a long time, neutrinos were thought to be massless. But over the last 15-20 years, we know that the neutrinos have tiny but non-zero mass. How tiny is about a few trillionth of a GeV. So understanding this tiny but non-zero mass will be subject of today's lecture. Again, let us recall that the electric charge of the neutrino is 0. The electron charge is -1. So the difference is 1 unit. Likewise, the upper quarks have mass 2/3, the lower ones have mass 1/3, -1/3. So difference is 1 unit. And that is due to the fact that each pair represents the isospin plus half and minus half projection states. So isospin difference of 1 unit shows up as charge difference of 1 unit. So each pair is an isodontate carrying isospin half. So neutrinos carry weak isospin half, takes part in weak interaction, but it doesn't carry electric charge, so has no electromagnetic interaction. The charged leptons have isospin half and also electric charge -1, so they take part in both weak and electromagnetic interaction. Quarks have isospin half, charge 2/3 -1/3. In addition, they have a color charge, so they take part in weak electromagnetic as well as interaction. Okay, so these are the 3 basic interactions which we have discussed in the morning. And the carriers of these interactions are called bosons. The carrier of electromagnetic interaction is photon, which is massless. Carrier of strong interaction is gluon, which is also massless. But the carrier of weak interaction, the charged W boson and the neutral J boson have huge mass, 80 J and 90 J. So the electromagnetic interaction between proton and electron is mediated by photon exchange. This is shown by this Fermion diagram. The analogous scattering of neutrino with proton is mediated by neutral J boson. This is called neutral current scattering. And the charge exchange scattering of neutrino with neutron going to proton and charge electron is mediated by charge W boson, which is called charge current scattering. In quantum field theory, incoming particle is same as outgoing antiparticle. So the same diagram describes neutrino on neutron to give a proton and electron. It also shows you the decay rate of neutrino into proton, electron, and electron antineutrino. So simply this is reversed here. Okay? And same process Also describe muon going to mu and electron antineutrino. These are simple diagram and self-explanatory, but if you still have any problem, let me know. Okay? So, neutron beta decay is the oldest and most obvious source of neutrino. This underlie all radioactive nuclear decays and underlie the source of reactor neutrino, rather reactor antineutrino. This muon decay is the main source of atmospheric neutrino. This charge current interaction of neutrino on neutron taking it to proton plus electron or muon, that is relevant for neutrino detection. Okay? And this is also comes in neutrino detection, like snow experiment, neutrino detection. Okay? Let us have a feel why the neutrino interactions are so weak. This is because of the mass of the exchange particle. W boson has mass of 80 J, so its range is S cross C over the response energy MWC square. S cross C we saw is 0.2 J Fermi over 80 J, so it will be 1 over 400th of a Fermi. That means 10 to the power minus 18 meters. Okay? So a neutrino has to come within a billionth of a billionth meter of either electron or quark to take part. Okay? So most of the time it passes through the body without any trace. In fact, a billion of solar neutrino is hitting every square centimeter of the skin every second, but they go without a trace. In fact, those billions go from one end of the arc to the other without a trace. Maybe 4 or 5 of them meet each other. Okay? So that shows how kind of elusive these particles are. That's why they are called ghost particles. Okay, we discussed God particle in the last class, now we are discussing ghost particle. Let us be a little bit more precise. This scattering, electromagnetic scattering amplitude that is shown here, okay, this scattering amplitude is described by the potential is square over R. That is familiar with you, Coulomb potential. Okay? That Fourier transform of that gives you the scattering amplitude, which is E square over Q square. Q square is the 4 momentum square being transformed. Okay? The analogous potential for weak interaction will be, instead of E, we call it G square over R, but because of the small mass, it has a very short range, e to the power minus R M. Okay, I have to use in small m. Okay, so this is in natural units, but if you want to use proper units, it's MW square over H cross C. Okay, so if you look at the range R0 comes in the denominator, will be H cross C over MW square C square, MW C square. So that is that. Clear? Okay, so if you take the Fourier transform of this, that will give you G square over MW square plus Q square. Okay. Now, for low energy process, which we will be mostly interested in, Q square be negligible compared to mw square. Okay? So this amplitude will be g square over mw square. Okay? So that is called the Fermi coupling. I think there is 1 over root 8 factor, there is a bookkeeping effect we have to take care. And that is 8 to the power minus 1. One thing is worth noting here, that we shall be mostly interested in q square less than mw square, where this amplitude becomes a constant, doesn't depend on q square, okay? It becomes a constant, that is the Fermi coupling constant, okay? But if q square becomes larger than mw square, okay, that means we have a neutrino scattering much more than 100 Z. Then of course you see there is no difference between electron scattering and electron scattering. Okay? Because the coupling strength are same. In fact G is equal to E over sin theta W. Sin theta W is about half. That is the width mixing angle. So this is about twice as well the electromagnetic coupling. Okay? So if your energy is much more than 100 eV, then your neutrino scattering cross section and electromagnetic cross section become the same. So that is called electroweak unification. So you achieve electroweak unification at the 100 J scale. Okay? The couplings are similar. The suppression is coming because of the mass of the W boson, but if you go to energy scales where the mass becomes small, okay, then you have electroweak unification. So that is the unification for which Grasso-Weinberg Salam. Okay, but mostly you shall be interested in the interaction at energy scale much smaller than W boson mass. So then it will be then the amplitude will be g square over mw square. Okay, or the Fermi coupling. Is it clear? Did I go too fast or are you all right? Huh? Okay, so let us proceed.
So if very high energy neutrinos, then they will be lost inside the arc. Maybe
Right. There is no difference between electromagnetic interaction.
At a neutron.
So if very high, okay, we are making it W square. We are making g square of q square. And g square is already bigger than a square. Okay. Neutrino chirality. The other Fermion chirality. Fermions have spin half, so they occur in two chiral states, left-handed and right-handed. Okay, right-handed means if it is going this way, and its spin is like right-handed screw, so the spin projection will be this way. Okay, and if it is going this way, but spin is like left-handed screw opposite to the direction of this. Okay, so this is shown here, right-handed Fermion or left-handed Fermion.
Sir, so what is the difference between chirality and helicity?
Very good. I was going to tell you that right now. Okay. The chirality and helicity are very closely interlinked. So let me spend a minute describing the difference. You see, uh, helicity is a frame dependent concept. Okay? Suppose observer is moving with velocity larger than the fermion, much larger. So then with respect to that observer, the fermion velocity will appear, go backward, okay? But the spin direction doesn't change. So that becomes the left-handed, okay? So that will depend on the frame of the observer. But chirality is intrinsic to the fermion. It is defined in that frame where it is traveling with extreme relativistic velocity, so that nobody else can overtake it. Okay? Okay? So there is a subtle difference, but in the process, loosely speaking, I shall be interchangeably using the two. So if you have any confusion, stop me there.
Physical observer, we can say chirality and the physical.
Sorry?
Because physical observable maybe.
No, what I said is the most correct thing and most understandable. Otherwise, you can make definition, but that doesn't add to your understanding. This is the understanding. Chirality is the helicity in that Lorentz frame where it is traveling with extreme relativistic velocity. Okay? Now, strong and electromagnetic interaction, they conserve parity. That means the left-handed fermion and right-handed fermions have the same strength of strong and electromagnetic interaction. It is left-right symmetry. Okay? Weak interaction break parity maximally. That means only left-handed fermion has weak interaction, right-handed fermion has zero weak interaction. If right-handed fermion had half the strength of interaction, you would say chirality is broken but not maximally, 50% broken. But here it is 100% broken. Okay? What it means? It means that only left-handed quarks and leptons have isodoublet, isospin half, they have weak interaction. Right-handed quarks and charged leptons have isosinglets, they have isospin 0, they don't have weak interaction. But they must be there because they have take part in electromagnetic and strong interaction. Okay, charged lepton have electromagnetic, quark have both electromagnetic strong interaction. So right-handed must be there, but they do not take part in the interaction. So they occur as isosinglets, isospin 0. Is it clear? Clear? But you see, neutrino has only weak interaction. It does not have strong or electromagnetic interaction. So there is no need for right-handed neutrino. Okay? So since there is no need for right-handed neutrino, in the standard model, one assumes that no, there is no right-handed neutrino. Clear? Now all gauge interactions, strong, electromagnetic and weak, conserve CP. That means if you make simultaneous parity transformation and charge conjugation, then it remains invariant. Okay? This means we have exactly opposite situation for antifermions. That is, the right-handed antifermions are isodoublets, take part in weak interaction. Left-handed antifermions are similar, do not take part in weak interaction. Okay? And there is no left-handed antineutrino in the standard model, like there is no right-handed antineutrino in the standard model. Sorry, right-handed neutrino. You see, antiparticle of right-handed neutrino is left-handed antineutrino. Okay? Because it is CP conservative. Okay? So in the standard model there is no right-handed neutrino, similarly no left-handed antineutrino. Is it clear?